In this video, we're going to look at some complex number expressions, 5 of them actually, and we're going to write them in the standard form, a plus bi, where a and b are both real numbers. So a real number plus a real number times I. So notice I doesn't have an exponent, or it has an implied 1 as an exponent. So clearly, number 1, I to the 275th power is not in standard form. So to simplify this and put it into an a plus bi form, we need to remember basically this. I to the 4th power is equal to, I'll break it down into I squared times I squared. I squared is negative 1. Negative 1 times negative 1 is 1. So, just as another example, if we take I, which is I to the 1 power, if I add 4 to it, I get I to the 5th. And that's equal, because I to the 5th is I to the 4th power times I. But I to the 4th power is 1. So this, if I add another 4 to the exponent, I to the 9th, is also, these are all three expressions are equal. I to the 13th, and so on. Now that's not going to help us for this problem. Well, it'll help us, but this isn't the answer. Now we need to figure, let me write this down one other way. I raised to the n power, where n is an integer, is equal to I to the n mod 4. So what that means is whatever this number is, it could be 275. If you just take 275 mod 4, you're going to get a remainder. Remember what mod is, you divide n by 4, and you'll get a remainder which will be either 0, 1, 2, or 3. So for us, the n is 275. And that means that I is equal to, I to the 275th is equal to I to the 275 mod 4. Well, if we divide 275 by 4, let's see, 4 goes into 200, and it goes into 72, so it would go in, 18 times 4 is 72, so it would go into 272. So 275 divided by 4 would leave us with a remainder of 3. 275 minus 272. So that is equal to I to the 3rd power. Well, I to the 3rd power, it still has an exponent, so we haven't simplified it completely yet. But I to the 3rd is I squared times I. I squared is negative 1. Negative 1 times I is negative I. So that's the answer to the first one. And by the way, negative I would, if this were 279, if I add 4, or if I add 8, or any multiple of 12, or any multiple of 4, or subtract any multiple of 4, I will also get this answer. All right, let's move on to number 2. 1 over I to the 5th. Well, I think I will first simplify just the denominator. What is I to the 5th? Well, I to the 5th is I to the 5 mod 4. Well, 5 divided by 4 is 1. 4 goes into 5 one time, with the remainder of 1. So that's simply I. So I to the 5th is equal to I. Remember, I is I to the 1. 1 plus 4 gives you 5. So 1 over I. Now, remember how we take a quotient like this. We multiply the top and bottom by the complex conjugate of the bottom. I has a complex conjugate of negative I. You can think of this as 0 plus 1i. Well, the complex conjugate is 0 minus 1i, or just negative I. So I'm multiplying these two fractions together, and note we're not changing the value because negative I over negative I is just a 1. So what do we get? The denominator turns into I times negative I. Well, I times I is negative 1. But if one of them has a negative sign in front of it, that's just going to give us a 1 in the denominator, and a negative I in the numerator, which we don't have to keep the 1 in the denominator, negative I. So the same answer as the first one. Interesting that I to the 275th power is equal to 1 over I to the 5th power. Let's see if we can get the third one as well on this piece of paper. Okay, number 3. We'll take a look at number 3. This is purely my preference. Notice this is not written in standard form. I don't have to convert it into standard form until the end. But I'm going to write it like 7 minus 2i, 5 plus 3i. It's just the way I like to do it. Obviously, this is the same as this. We wrote it in standard form. If you FOIL this out like we normally do, you're going to get exactly the same answer as I get here, because 5 plus 3i is 3i plus 5. But we'll write our final answer in the form of a plus bi. So when I FOIL this, I'm going to get 7 times 5 for first. Outer, that's the f. Outer is going to be 21i. Inner will be minus 10i. And the last, well, let's see, it's going to be a negative 6i squared. But remember that I squared is just negative 1. So negative 6 times negative 1, this whole thing right here is a positive 6. And as you recall, when you FOIL it out, when they're both in standard form like this, the f and the l, first and last, will give us our real numbers, and the 2 in the middle, the o and the I, will give us our imaginary part. So finally, I'll combine the 35 and the 6 for 41. And the inner would be 21i minus 10 would be 11i. Okay, so that's the first 3. And now I think I'll need another sheet for numbers 4 and 5. Maybe I can get them right here. Number 4. Let's do it right here. Okay, rather than rewriting it, maybe I'll just FOIL out the top first. So 4 times 1 is 5. That's the first. I'm going to jump to the last because that'll be another real number. Last times last. Negative I times negative 3i is positive 3i squared. But I squared is negative 1. So that's a minus 3. Oops. 5 minus 3. Oh, I'm sorry, it should be 4 minus 3. Goodness. 4 times 1 is 4. So that's going to be the real part, and then the outer and inner will give us the imaginary part. Outer is negative 12i. Inner is negative 1i. Negative 12 minus 1 is negative 13i. All right, now let's do the denominator. We'll keep it the way it is. Let's simplify the top. 4 minus 3 is 1, so we get 1 minus 13i. Over negative 1 plus 2i. So we have a quotient again, and what do we do when we have a quotient, complex over complex? We multiply top and bottom by the complex conjugate of the bottom. Negative 1 minus 2i. Like so. And the beauty of this is that the numerator is going to be a real number now. The outer and inner will cancel out when we do our FOIL. So we just need to do the first and the last. We get a positive 1 and a positive 4. And remember, when you multiply complex conjugates, you can just take the real part and the imaginary part, square each one and add it. 1 squared and 2 squared is 5. Negative 1 squared and negative 2 squared, it's 5. So I'll do the denominator first. And now the numerator. When we FOIL this out, I'm going to get first is going to be negative 1. Last is going to be negative 13i minus 2i. That's positive 26i squared. Positive 26i squared is a negative 26. All right, that is the real part. Now let's do the outer and inner to get the imaginary part. Negative 2i for the outer, positive 13i. So positive 13i minus 2i is going to be 11i. Oops, not very clear there. That's 11i. And that's the answer, although we're not simplified. That's simply equal to negative 27 over 5 plus 11 over 5i. Like so. All right, well, number 5 looks pretty simple. All we're doing is FOILing out 1 plus I radical 3 times, I'm going to go ahead and rewrite this in the standard form, radical 3 plus I. Again, if you don't do it that way until the end, you're going to get exactly the same answer. All right, let's FOIL this out. So f is going to give us a radical 3. First, the last, which will be a real number, the last is going to be radical 3 times I squared, which is a negative radical 3. That's the real part. Now we'll do the outer and the inner. The outer, oh, actually, there's one change. I wrote this problem incorrectly. That's supposed to be a complement over the whole thing. I'll worry about the complement at the end. Okay, so this is the F, the L. Now I've got to do the O and the I. Outer is I. Inner is radical 3 times radical 3i. Well, radical 3 times radical 3 is 3, so that's going to be 3i plus 3i. And that is equal to 0 plus 4i under the complex conjugate bar. And this is very simple. What's a complex conjugate of 4i? Well, 4i can be written as 0 plus 4i. What's the complex conjugate of this? You replace the plus sign with a minus sign. So we're going to get negative 4i. And that is the end of the problem.